talk about optimization. Last class we focused on finding local extrema. So those are high points and low points in their neighborhood, right? Today we're going to find global extrema, the highest point and the lowest point on an interval. Okay, so for this function pictured, should look familiar. This is from the activity that you did last class. I want to find the x-coordinate of all global extrema on these various intervals. Okay. So from A to J. So on the interval from here, A to J here, what is the highest point? Where does it occur? Oh, okay. H, oh, that's I and J's like over here. Like that, maybe. Okay, so my highest point then happens at J. So global max at x equals J. And where's my minimum, my lowest point on that whole interval? D. Global min at x equals D. Good. Now what if you just look at the interval from C to E? Just this interval here. What is the highest point? C. Global max at x equals C. And the very lowest point in that interval? D. Global min at x equals D again. Okay, what if I look at the open interval from C to E? So this time I'm not including this endpoint of C. What's the highest value of the function in that interval? Just to the right of C, okay? So what number is just to the right of C? Maybe 0.1 to the right? C plus 0.1? Smaller than that, C plus 0.01? You can keep getting smaller and smaller, so I can't pick a specific number that has the highest point, because I can always get closer to C. So in this case, I have to say there's no global maximum. Because if I try to pinpoint where it is, I can't, right? I start saying, well, if C were in the interval, it would be at C, but C's not in the interval. And the next highest point is just to the right of C, but I can always get closer to C. So I can't say right where that maximum would occur. So it's this open interval thing makes it so that I can't find a global max. Is there a global min on that interval? D, yeah. All right, how about negative infinity to infinity? Do I have a global max? No, because it just keeps going up forever to the right. Do I have a global min? No, because it keeps going down forever to the left. So this one has no global extrema. All right, so here's a theorem that's intuitively obvious but hard to prove. It's called the extreme value theorem. It says if a function is continuous on a closed interval, so you draw it without picking up your pencil, then the function has to have both an absolute maximum and an absolute minimum on that interval. It's a closed interval and it's continuous. It has to have a high point and it has to have a low point. What are the two kinds of points where a continuous function on a closed interval could have its absolute max or its absolute min? No. Look at the examples. Crucial point, you mean a critical point? Yeah. At a critical point where you have a horizontal tangent line, right? Or where else did we sometimes have the maximum or minimum? The end point of the interval. Okay, so those are the two kinds of places you can find a global max or a min. At a local max or a min, or at a critical value, or the end point of the interval. So if you want to find the absolute extrema, find all the critical points, evaluate the function at each of the critical points and at each of the endpoints of the interval. The biggest value is your global max, and the smallest value, y value, will be your global min. So for example, without using a graph, I want to find the absolute extrema, the highest point and the lowest point of f of x on the interval from 1 to 5, closed interval from 1 to 5. So I could have an extreme value at any critical value, or at 1 or at 5. Right? Those are the places where my extreme values could happen. So let's find critical numbers. Where do those happen? Where the derivative is 0, or where the derivative is undefined. But this is a polynomial. Its derivative is never undefined. So I'm just going to set the derivative equal to 0. Okay, so that would be 6x squared minus 30x plus 36 equals 0. I'm just going to divide everything out by 6. And so I have x squared minus 5x plus 6 equals 0. And that would factor to x minus 6, x minus 3, x minus 2. And so x equals 2 and 3 are critical numbers. So I could have, those are possible locations of a local max or a local min, or a global max or a global min. And I don't care, or not that I don't care, I don't need to figure out if those are local maxes or local mins or neither, because I'm on a closed interval and I just want the highest point and the lowest point. So I just need to know the function value at these two, and at 1 and at 5, the highest point is my global max. So I'm just going to take f of 1 from the endpoint of my interval. So that's going to be 2 minus 15 is negative 13 plus 36 is 23. F of 2, I might need a calculator. So I'm just going to type my function here. 2x cubed minus 15x squared plus 36x. Let's go to my table. Check the 1. Yep. 2. I get 28. F of 3. 27. And f of 5. The other endpoint of the interval is 55. So on the interval from 1 to 5, what is the highest y value? 55, and it occurs at x equals 5. So we have a global max at x equals 5. And what's the smallest y value? 23. So that occurs at x equals 1, so we have a global min at x equals 1. So global max of 55 at x equals 5, and a global min of 23 at x equals 1. So it turned out the endpoints of the interval gave my global max and my global min in this case. So let's look at the graph of this thing and just make sure that this is right. So let's see, my window, I'm only interested in the interval 1 to 5, so maybe I'll go 0 to 6, just so I can see everything. And my y values are like 23 to 55. I think that those are my global min and my global max. So those would be a good choice to choose my y range. So maybe I'll go like 20 to 60. Okay, so at 1, let me just take a picture of this so I can draw on it. All right, so my interval that I'm interested in is 1, 2, 3, 4, 5 to 5. And I want the highest point and the lowest point in that interval. So the possible places where I could have a high point or a global max or a global min are places where the derivative is 0, which happened at 2 and at 3, right? We've got some horizontal tangent lines there. It's like there's a little max and a little min. Or the endpoints of the interval here and here. So in this case, the endpoints were the global min and the global max, even though we had a local max and a local min in between. Okay, so let's think about this problem that we talked about on the very first day of class. Had to do with how a lake freezes. Right, when a lake begins to freeze, what part of the lake freezes first? The top, yeah. Okay, so for temperatures from 0 to 30, the relationship between the volume of 1 kilogram of water at temperature T is this cubic, right? So the volume of water changes as temperature change, which means its density changes. And so basically, there was this magic temperature that made water float to the surface so that it could freeze at the top. Does this sound familiar? Okay. So the volume of water at a given temperature is given by this cubic function. Okay, so we want to enter this equation to the calculator, find a good window. Let's see. Negative 0.40. Oh, okay. 679x cubed plus 0.008504 x squared. Okay, and then so this is volume at given temperatures, and temperatures going 0, we're measuring 0 to 30. That's the domain of this function for volume. So I'm just going to go 0 to 30 for x. And then for volume, I'm going to use this little table to help me figure out some y values, right? So if I go to my table, if I put in 0, my volume is 999.87, and if I put in 30, my volume is 1003. So maybe I'll go like, I don't know, 990 to 1010 or something for y. It's just a first guess. All right, so here's my graph. It does look like it has a minimum somewhere over here. Maybe I'm looking at more x values than I need to. Oops, and I only meant to go 0 to 30. Why did I write 60? Yeah, now it's a little clearer that we have a minimum somewhere in there. Okay, so then on the first day of class, I said, here's a seemingly unrelated exercise. Solve this quadratic equal to 0. Now that we've had 2/3 of a class of calculus, where did that quadratic equation come from? It's the derivative of that volume function set equal to 0. Why would I take the derivative and set it equal to 0? To find the critical numbers, which is where that minimum will be located. So this is V prime. We set it equal to 0, do the quadratic formula. So negative b 6. We'll do plus negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. .97. So it's 4 degrees was that magic number where you get minimum volume. So you get minimum volume, which means maximum density, right? Your water's taking up the least amount of space, which means it's most dense, and 4-degree water sinks to the bottom. Right? So a temperature just above freezing sinks to the bottom, which means that life can survive at the bottom of a lake under the ice. All right, so fill blank with your answer. Store all of your answers as A, B, and C. All right, so now I'm just going to get a global. I want to get a global max and a global min for this function on 0 to 30. So I just have to evaluate the function at each of these values. Go to my table. I've got 0, 30, and 3.97. So this is 999.87. This is 1003.8, and 3.97 gives me 999.74. So the volume of water has a global minimum on the interval from 0 to 30 degrees, has a global minimum of 999.74 cubic, whatever the units were, at 3.97 degrees Celsius. What were the units? Cubic centimeters. All right. Slightly different when you're trying to find a global max or a global min on an open interval. When you're on a closed interval, find all the critical values, take them and plug them into the function as well as the endpoints of the interval, and just pick the highest and lowest. But if f is on an open interval, there may or may not be a global max or a min. So in this case, find the value of the function at the critical points, but also look at the behavior of the edges of the interval, right? Close to that open parenthesis. So sometimes that might be towards plus or minus infinity. Sometimes it might be close to a number like C in one of our earlier examples. So for example, I want to find the absolute extrema, the global max or min of this rational function on all real numbers, negative infinity to infinity. So first I want to find any critical numbers. Those happen when the derivative equals 0, right? Or when the derivative is undefined. So first thing I should do is find g prime. Any strategies for g prime here? I could rewrite that as x squared plus 1 to the negative 1. Yeah. And then I could use the chain rule, the power rule and the chain rule. Bring the negative 1 down, so I have negative x squared plus 1 to the negative 2. So apply the power rule to my stuff, but then I have to multiply by the derivative of the stuff, which is what? 2x. Good. So g prime of x, if I simplify this, ends up being negative 2x over x squared plus 1 squared. All right, so critical numbers happen when g prime of x equals 0 or g prime of x is undefined. So I have a g prime is a fraction. When is a fraction equal to 0? When the numerator is 0. And that happens when x is 0. And g prime is undefined when its denominator is 0. So x squared plus 1 equals 0. Can that ever happen? No. X squared can never equal negative 1 because when you square something, it's always positive. So that equation has no solutions. All right, so we've got a critical number at x equals 0. Could be a max, could be a min. I need to, a local max or a local min. I have to think about what happens at the edges of this interval as x goes to positive infinity and x goes to negative infinity. What happens to the function g as x goes to infinity? It gets closer to 0. That denominator is going to get really big, so the fraction is going to get really small. All right, so I need to know what happens to g at 0 and at the endpoints of the interval. So g of 0, write this down here. G of 0 is 1, right? Just plug a 0 in there. And then I also need to know the limit as x goes to infinity. You guys are being very distracting today. Maybe it's me, but if you could stop the talking, thank you. The limit as x goes to infinity of 1 over x squared plus 1, we said is 0. So at the endpoints of the interval, it's heading towards 0. And at the other end of the interval, the other edge, what's that limit? Also 0, because when you square a negative, it becomes positive anyway. So this is also heading towards 0. All right, so I know I have a extreme value, possible extreme value g at 0. And at the endpoints, the function is approaching 0. So what can I say about the point 0, 1 on the graph of G? Global max. Yep. It's the only possible local max or min. So I've got this point here. And I know that my edges of my graph head down to 0. And I know that it's positive because my function values will always be positive. No matter what I plug in, I'm going to have a 1, which is positive, divided by something positive. So my function probably looks something like this. And I have a global max. All right, so as another example, when you cough, your windpipe contracts, means gets smaller, and the speed, v, with which you expel air depends on how much your windpipe contracts. So the smaller it gets, the faster air comes out when you cough. So your velocity depends on the radius of your windpipe. So we're going to let A be the normal resting radius of your windpipe when you are not coughing, right? So we want to look at an interval from 0, meaning completely closed, to A, your resting radius of your windpipe. All right, so we're going to look at this interval where the radius of your windpipe is somewhere between 0, completely closed, and A, completely open at its resting state. The velocity of the air that you expel when you cough is given by this function. K, so just some constant of variability, times A minus R, so the difference between your resting state and how closed your windpipe gets when you're coughing, times R squared, the radius of your windpipe when you're coughing. So what value of R maximizes speed? And for what value is the speed minimized on this closed interval 0 to A? So before you start working on it, what value do you think the speed is going to be minimized at? Slowest that air comes out. A, yeah, because you're not actually coughing, right? So it's going to be coming out at 0 or, yeah, it's got to be 0. Or some slow, regular breathing. Maximized, what do you think? Is it at the other endpoint of the interval? At 0? Right, if it's 0, nothing's coming out, right? Your windpipe is closed. So you're gonna have a maximum somewhere in between 0 and A. All right, so I have a function on a closed interval, and I want to find the global max and the global min. Right, I'm trying to maximize speed and minimize speed. Variable is R, the radius of your windpipe. All right, so if I'm trying to find global max and global min on a closed interval, right, it's closed because of these or equal to's. I need to find any critical numbers, and I'm going to evaluate the function at critical numbers and the endpoints of the interval. So critical numbers I find by taking the derivative and setting it equal to 0, or places where the derivative is undefined. So v prime of r equals 0, or v prime undefined. All right, so when I'm taking v prime, I have a couple of options. I could use the product rule, or I could multiply it all together and then take the derivative. So if I distribute the r squared and the k, I get k(a)r squared minus k(r cubed. And then I can take the derivative real quick, no product rule. So v prime of r is going to be, ka is just a constant, just some number, k times a. So I'm going to bring the 2 down, so I get 2k a r to the first. And then I have minus, bring the exponent down, 3k r squared. So there's my v prime. That is just a polynomial. It's just a quadratic. It's never undefined. So I just have to set it equal to 0 and solve it. And what am I solving for? There's 3 letters in there. Which one am I solving for? R. Good. A and k are just numbers. I want to know what r value makes the function 0, the derivative 0. So I've got an r in both terms here. So I could factor out kr actually. And I'd be left with 2a minus 3r. So once I've factored out kr, now this is the product of 2 things. The answer is 0, so I can set each factor to 0 and solve each one. So in this case, r would have to be 0. So I have a critical number at 0, which is also an endpoint of the interval, so I would have tested it anyway. Okay. Or I get 2a equals 3r, so a, solving for r is 2/3 a, another critical value. So then I have to check my velocity at each endpoint of the interval, 0 and a, and at my critical value, 2/3 of a. Okay, so my velocity at 0 when r is 0 is going to be 0, right? Because I'm plugging in a 0. 0 squared is going to be 0 times what, doesn't matter what else, it's 0. Which makes sense because if your windpipe is completely closed, no air is going to be able to come out. So the velocity is 0. And if I plug in an a, right, this middle term, the a minus r, replace the r with an a, that whole thing becomes a 0. The whole function becomes 0. Okay, so that makes sense. The speed that you're coughing at, the speed that air comes out when you're just in a normal resting radius is 0. So 2/3 a is going to have to be my maximum. So when 2/3 of a is your normal resting radius. So when it is 2/3 of a, you're going to get maximum velocity. And that would be something. So 2/3 of a, I guess I'll write it out. K times a minus 2/3 a times 2/3 a squared. So this is k times 1/3 of a times 4/9 a squared. So 1/3 times 4/9 is 4/27, which is not reducible. So I have 4/27 and a k, and then I have an a cubed. And we know a is positive, k is positive. This is some positive velocity. So this is my max, global max. All right, any questions? This is a minus. And so 1a minus 2/3 a is 1/3 a. All right, so I have this interpreting graphs using calculus part 2. Okay, so this is similar to the activity I had you work on last class, except this time that function that I gave you is f prime, not f. So last class we went off the assumption that this was the graph of f, and you answered all these questions about f, f prime, f double prime, f triple prime. Now I'm giving you a graph of f prime, and you're going to answer questions about f, f prime, f double prime, and f triple prime. Okay, so you can work on that.